So let's look at a control chart. And so here's an X chart, an X bar R chart. And there's an upper control limit here. And there's a center line, which is usually the average, mean, or median. And we use mean for average and average for mean. But you know, most folks don't use statistical terms like mean, and mean means something different to them. And then there's a lower control limit. And all of these control limits are calculated from your data. Right, the upper control limit depends on how far each point is above or below the center line, and there's a whole bunch of formulas that make that happen. Now, unlike other folks, I don't think you have to know the formulas to do this, because software will do all the formulas for you. What you need to know is how to read the chart, okay? So this is an important thing. Now, 99.7% of all of the data points are going to fall between the upper and the lower control limit. That means 997 out of 1,000 are going to fall in here. So if you have one point like this red one up here that falls above the control limit, and we only have 20 or 30 points here, that's pretty unlikely. So this point might actually be considered to be out of control. And then we have a whole bunch of points here that are below the center line. Well, that's kind of an odd thing. And so here we have 8 points in a row below the center line. That's another type of potentially out of control condition. And control charts are just designed to tell you to look at this, check it out, and see if this is something funny going on and we need to adjust the process. Because what it looks like is we were going along fine here, we went a little wiggy here, and then we changed there. So what's going on, and what do we do with that? Now, in statistical process control, there's these two ideas. One is called common cause variation, and the other is called special cause variation. And here you can see the points are just kind of ziggy-zagging around, you know, and they're actually all blue, which means they're in statistical process control up to that point. That's common cause variation. Common cause, you know, think about your drive to work every day. If you drive to work, it might take you a little longer, a little shorter, but you can always do it in a certain period of time. When I was driving to work downtown, it used to take me anywhere from 22 minutes to 30 minutes, unless there was a snowstorm. You know, in a blizzard or something like that, or an accident, that leads us into special causes. So common causes are what you normally experience, and special causes are out of whack things. So in Denver, if we get a 2-foot blizzard, guess what? You know, we can have a special cause. Or if it's, I'm only going to work on the weekends when there is no traffic, or I'm always driving in at 4 o'clock in the morning, all of a sudden my drive time is a lot less. There's some special causes in there as well. So what we want to do is investigate what are those special causes and get rid of those first, and then we can come back and work on the common cause variation. Now you want to do that before you start getting into capability. Until you have a process that produces consistently, it's a little hard to you know, come back and fix what your customer really wants. Now, there's a number of rules that apply in here based on statistics, and you don't need to know all of these because the QI macro software will draw them all for you. All right, so any 1 point above the upper control limit or below the lower control limit, 2 out of 3 points above 2 sigma, the 2 sigma line, 4 out of 5 points above 1 sigma, 8 points above, 8 points below, runs on either side here. Because essentially 2/3 of all data points should fall between 1 and -1 standard deviations, or 1 sigma, around your average. Well, that means it's kind of unlikely that 4 out of 5 points would be above it right in a row, right? Or 2 out of 3 points above 2 sigma. That's kind of unlikely, and 1 point above 3 sigma. And so these rules help guide us to do some analysis and figure out, do we have a special cause and do we need to investigate? And again, the QI macros will draw all these charts for you, identify all these points, and then you can figure out, should I go do special cause analysis or not? Now once you have a special cause, you know, one of those points above or below the control limits, how do you determine root cause? Well, you can go in and ask the 5 whys. You know, well, why did this happen? Well, there was a blizzard. You know, why did it take so long to get to work? Well, there was a blizzard. And why did it take so long in a blizzard? Well, everybody drives badly and it's slow and there's lots of accidents. And well, why does that happen? Well, it snowed. Okay, there's not much you can do about that. But In other situations, there might be a root cause. And so what would we do to fix that, to eliminate that special cause and get it out of our process so that all we have is common cause variation? You could also use the Ishikawa or fishbone diagram. You eliminate that special cause variation, and then you can come back into doing your problem solving to eliminate the common causes of variation. So that's a little bit about stability. How do we predict the output of the process, and is it predictable and consistent? Get rid of the special causes first, and then come back and fix the common causes of variation. So here's an example of some data, and this is the bursting strength of bottles. So let's say we're in injection molding some bottles, and we have an upper spec limit and a lower spec limit of 346 and 200. Well, we could take this data with the QI macros, just select it, click on the chart wizard, and it'll start prompting us. And so I'm going to just put in our bursting strength of bottles here. And the X charts produce a range chart, which shows the variability between each one of these subgroups, and also the actual chart itself. So this is the range between groups here, the range between this group and that group and the next group. And this one is actually showing our variability. Now, since there's no red points here, this means our process is stable. We can count on a bursting strength of 264 and varying between 220 and 308. All of these things can be handled with statistical process control. So enjoy practicing statistical process control. In the QI macros, the control chart data is actually out there in our QI macros test data, so you can try this on lots of different applications. We have automotive and standard manufacturing and healthcare data. All of those things you can practice in there and get a feel for this, and then start using it on your own data. And that's SPC Simplified.